So as far as the bullet points are concerned for the bomb calorimetry, remember if we discussed about this, how these are often used for combustion reactions. It doesn't matter I gave you the bullet points or not, because some of us aren't going to get them anyway.
Your bullet points, yeah, because
I just said it for the second time. I know.
I wasn't even talking.
Often used to study combustion reactions. And the other thing what I said was that you have to determine the heat capacity of the bomb first. Those of you that paid attention the last time we talked about this may remember these ideas. Okay? All right, so the example that we're looking at here is a 0.5865 gram sample, which I believe, no, you have that, of lactic acid is burned in a calorimeter. Now, sometimes, as I stated when we started this problem last time, it wasn't recorded, so I'm doing it again. God, it's going to put us behind. Someone else had already done the experiment to determine the heat capacity of the calorimeter. Sometimes you will have some information with which you can calculate the heat capacity of the calorimeter. Remember, heat capacity is energy per degree Celsius. Anyway, so someone had done the experiment, and it turns out the heat capacity of the calorimeter is 4.112 kilojoules per degree Celsius. In the experiment in which we were testing the lactic acid, we find out that its temperature increased from 23.10 to 24.95. Obviously, an exothermic process. It's we're combusting. Wants to know the heat of combustion of lactic acid per gram and per mole. So, how are we going to find out how much heat was released by the reaction? Well, that's where we take, as I said before, you can see the equation written up there. It's negative C of the calorimeter times the change in temperature. Okay? So, what's the heat capacity of the calorimeter? Well, it's 4.812 kilojoules, I believe, right? Degrees Celsius, per degree Celsius. Now, there's a negative sign there. We'll talk about why here in a second. And we see that the temperature of the calorimeter changed from 23.1 to 24.95. So therefore, the delta T is going to have a positive or a negative value. It's going to be a positive value because final minus initial. And it looks like what, 1.85? Okay, so 1.85. What the negative sign does, all that does is switches us from looking at the system, or sorry about that, from the surroundings to the system. Because remember, we're worried about the system. Anyway, when you do the calculation, you come up with negative 8.902 kilojoules, because our degrees Celsius cancel out. Now, we're going to be looking for both the energy released per gram and the energy released per mole. So, to do the gram, all we're going to have to do is what? Divide this by the mass, which I forget what it was. 0.5865 grams. Okay. And essentially double that, or a little bit over double that, so we're going to get 15.18 kilojoules per gram. Or, if we want the enthalpy, which is typically given in kilojoules per mole, the first thing we have to do is, or the next thing we have to do is convert this to moles, which is relatively easy. It's 90.09 grams, by the way. Okay, and we do a similar calculation. We get negative 1367 kilojoules per mole. So negative 15.18 kilojoules per gram or negative 1367 kilojoules per mole. It's not hard. Why do you have my brain?
I don't know.
Okay. This is why I keep my door locked during 5th and 6th period typically. All right. Any questions? All right. The next piece is one of 3 different ways that we are eventually going to learn how to calculate the enthalpy of chemical reactions. I'm really trying to be very clear on this. We're going to learn 3 different ways of finding the enthalpy of a reaction. Okay? 2 of them are going to happen in this chapter. 1 of them is going to happen when we get to the chapter on bonding. So this is going to be after Christmas. Okay? That one is the least precise of the 2 anyway. It's more of a, hey, this is a pretty good estimate. The 2 that we're going to learn in this chapter are actually fairly useful things. In fact, the lab that we are going to do is actually the one I'm going to show you now. Okay? This next piece is called Hess's Law. Very standard, very typical way of calculating the enthalpy of a reaction. In this case, what we're doing, we're assuming that, or Hess's Law states that, the change in enthalpy is the same in a chemical reaction, whether the reaction takes place in one step or a series of steps. What that means is change in enthalpy is a state function. Doesn't matter how many, so we're using the idea that state functions, it doesn't matter how many steps it takes to get there, you're going to end up with the same result. You've already been kind of introduced to this idea. The whole half reaction method that we did for balancing redox reactions. Essentially what we're going to be doing is we're going to be looking at 2 or more different chemical reactions in which their enthalpies are known. We're going to manipulate those equations by either multiplying them by coefficients, if we have to have more of something happening, or reversing the equations. Okay, so very similar to the redox reactions, if we reversed a reduction potential, it became an oxidation and we changed the sign. Okay, same thing here. If we have an exothermic process and we reverse the reaction, the value for the change in enthalpy is going to be the same, except the sign is going to be different now because we reverse it. Does that make any sense? However, remembering the difference between a reduction potential, which is an intensive property, and energy calculations, which are extensive properties, if we have to multiply by a coefficient to get things to balance out, we are also going to have to multiply the enthalpies. So there's the distinction between the electricity stuff we're doing and the enthalpy stuff we're doing. So I just kind of covered steps 1 and 2 there. Now let's just walk through a very simple example. Now here's what would happen. Let's imagine that you have created, as a chemist, have created this wonderful new chemical process, chemical reaction. It's never been done before in the history of the whole worldwide stuff, okay? Wouldn't it be nice to have somewhat of an idea whether, 1, it was going to be endothermic or exothermic? Do you have to account for it being so exothermic that you have to cool it down as it's going on, or is it so endothermic that you need to provide enough energy for it to go? Is this making any sense? So 1, it'd be at a basic level, is it endothermic or exothermic? And 2, what is the extent to which it's endothermic or exothermic? Because if it's just a small, warms up a little bit thing, you don't really care about it too much. But if it's going to be one of the most exothermic things in the history of the world, you better be prepared for that. So this is why we're doing these things. However, the reaction's never been done before. So now how are we going to find out what's going on? Well, what we can do, and you will never be asked to create these. These will always be provided for you. But what you do is you take a number of reactions that are known and that the enthalpies are known, that if you manipulate those by adding them up, flipping them, reversing them, whatever, and add those up, then you'll get your reaction that you're looking for. Well, I think when I first introduced this stuff, some people panic, like, oh my gosh, how am I supposed to come up with these reactions? You'll never have to. They'll always be provided. Here's the example. Given the following reactions, I give you, what, A and B there, right? Both of those reactions are known. Okay, they've been studied for a long, long time. They're known. And so the first one, as it says there, is 2N2O. States of matter you're really going to have to pay attention to for some of these. Decomposing into oxygen gas and 2 nitrogen gases. And the enthalpy for that reaction is negative 162 kilojoules per mole. And there's one thing that you do have to kind of be careful of. Whenever you're given enthalpies, it's presumed that they're kilojoules per mole. They don't always write the per mole part. So if it's a delta H, it's kilojoules per mole. The other reaction we're going to consider is 2 NH3s, ammonia gases, plus 3 N2Os, yielding 4 N2s, plus 3 H2O liquids. Enthalpy for this process is known to be negative 1012 kilojoules per mole. So these are the 2 reactions that are known. So what we do is pretend that, hey, we've never seen this other reaction before, so our target reaction is this. 4NH3 plus 3O2, giving us 2 N2s plus 6 H2Os. We have currently absolutely no idea what its enthalpy is. So what we're going to do is use the 2 reactions that I've provided up here, manipulate those in such a way that they add up to that final reaction, and then adjust the enthalpies accordingly. A process you guys have kind of done before with the electrochemistry stuff. So, here's what we need to do. One of these might have to be reversed. How do you figure that out? Well, there's any number of ways you can figure that out. But is there one reaction that we're definitely going to keep the same direction? The second one has to be, because we're looking for liquid water as a product. The only one that has that is this. Also, we have to have ammonia as a reactant. The only one that has ammonia as a reactant is this. Would you guys agree? Great. Now, do I have the right amounts of these? No. So what am I going to have to do? Looks like double it, right? So let's double this reaction. And remembering, because it's an extensive, enthalpy is an extensive property, we're also going to have to remember to double the enthalpy provided, which is the different thing that we never had to do with the electrochemistry. What about the top reaction? Say this again. Why?
Because the O2 is on the wrong side.
Yep, the oxygen's on the wrong side. It needs to be as a reactant, and we need 3 times as much, right? Now, I'm going to do this. You guys can do different things with it. Right now, I'm just going to say multiply it by -3. Or let me do it this way. Now, the negative sign just means reverse the reaction. Many of you, especially early on, like now since you've never done one of these before, might feel better if you just go ahead and rewrite the equation. I think that's going to help a lot of you out early on. So, and then also remember that we have to do the same thing over here. So, I'm just going to rewrite the equation. So now we're going to get 3 O2s plus 6 N2s and 6 N2Os. Do you guys agree with that? And now it's just a matter of combining like terms, canceling species out that need canceled, and blah, 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 blah. So I'm going to get rid of this so that we don't look at it anymore. And just go through and start combining things up. Well, I see 6 N2Os and 6 2N on the reactant side and 6 N2Os on the product side. Those cancel. You guys happy with that? I see 6 N2s and I see 6 N2s on the reactant side, 4 N2s on the product side, which results in a net of, I lied, 8 on the product side, 6 on the reactant side, which results in a net of 2 on the product side. Six oxygens on the reactant side. I lied. 3 oxygen molecules on the reactant side. Okay. That top equation's done. So now we've got what? 4 ammonias and 6 H2Os. Everyone hunky-dory? So we have the target reaction, so we manipulated our equations correctly, whatever that was, and now we just have to do the enthalpies. So we multiply this one by -3, we multiply this one by 2, whatever the math comes out to be. Maybe someone's already done that. Pardon? Yeah, okay. $1538?
I got 1532.
So did I. And what sign? Yep. 1532, correct? And negative 1352 kilojoules per mole of reaction. Yeah, it's okay. Oh, my bad then, huh? Sorry about that. No, I'm going to fix it. I'm going to fix it. So you were right with the information that was provided, right? Okay, that's not too hard. Would you guys agree? If we have time, we may or may not. Maybe I can or give you guys one to try on your own, see how it happens. But honestly, it's now you might run into 4 or 5 equations that you guys have to manipulate, but it's the same idea. You just keep flipping things, multiplying things, sometimes dividing things. Depends on what you're given. It's just a matter of manipulating them. All right. I do want to go to the next part, which is the second way of determining the enthalpy of a reaction. You're going to need a textbook in front of you at some point in time. Okay, a chemistry textbook, AP chemistry textbook at some point in time. Joe had his physics book sitting on top, that's why I said that. I just got an email back from their advisor, said she only has like 6 or 7, 6 or 7. Although she's going to have a full team, yeah. We won't, but that's all right. Maybe we can talk Kayla into coming. What? Hey, when did your brother graduate? What? When did your brother graduate? 4, 3. What year is he?
Wait, they graduated
Who's they?
Well, my brother's in her grade.
Oh, okay. You know, I think they were in the same class. No, I think about that.
16, my sister graduated in 2015, and they're 1 year.
Okay, thank you.
He graduated early.
Yeah, I know. You kind of lose track. I get that. Okay. Anyway, moving on. And again, I'm emphasizing there are 3 ways that you're going to learn in this course to calculate enthalpies of reactions. 2 of them are going to happen in this chapter. We just did the first one, Hess's Law. You guys already have a little bit of familiarity with the process. The second one is something called using standard enthalpies of formation. Okay? Or, as you can see, the little symbol that I put up there, the delta H sub F with a little superscript 0. That superscript 0, we're going to start running into this more often, means standard state. And does everyone remember what the standard states are? Because we've run into the E cells also at standard states. Is that 1 atmosphere of pressure if it's a gas,
1 molar concentration.
1 molar concentration for solutions, 25 degrees Celsius for temperatures of all the substances, and if it's a solid, it's the liquid or solid. I know, that's the weirdest one. It's weird, I get that. But oh, hey, here we go. You're looking right off of there. Good thing we've already done that, huh? All right, moving on. At some point in time, if you could, now would be good, turn to page 276 in those books. And again, if there's only 1 book per pair, that's fine. What you guys need to do is find 2 people and tell them to get their books back into here as soon as possible. Those people are Gracie Schaefer and Brian, whatever his name was. Wharton. What I'm saying is those 2 people still have their books. And if they return those books, then you would all have something to look at. Anyway, on page 276, you'll see a small list of standard enthalpies of formation. You know what I'm going to have happen here? Sorry to do this to you, but, well, no, it's the fact that all 4 of you have a book. Oh, well, sorry.
No, just like,
I got you. All right, so anyway, you'll see a small list of standard enthalpies of formation. Notice that, for example, look at the bromine, the liquid bromine. Bromine's a liquid. What does it take to get bromine to be a liquid? How much energy? 0, because it's already a liquid at those conditions, 1 atmosphere of pressure, 25 degrees Celsius, okay? What would be another example? The graphite. Chlorine gas would be an example. Nitrogen gas. Oxygen gas. I mean, you know what I'm saying? If they already exist as these things, their standard enthalpies of formation are 0. But you'll notice that the rest of them are either exothermic or endothermic to some degree. Okay? If you can turn to the index, A5. Your book's kind of weird how they do their index. Not the index, but the appendix. Thank you. A. Get it? A. Appendix, page 5. Now, listen. A5 through A10. Do you see where I'm going with that? Okay, I lied. Nope, I was right. Now, I do want to show this to you. When you're in the appendix, the A5 through A10, you'll notice across the top there's actually a number of different quantities that are provided there. The first one probably is the enthalpy, right?
Yeah.
Delta H's. Then you're also going to see a delta G, which is called Gibbs free energy. That's what's going to happen when we move over to chapter 18. And then you'll also see a delta S, or not a delta S, you're just going to see an S, which is entropy, which is also what we're going to cover in chapter 18. Currently, we only care about the enthalpy, the delta H's. Later on, we will care about all of them. Okay, moving on. So we're going to need to refer to this to do the next couple of things. So all you do is use that little equation over there. Remember, delta H always means final minus initial. So, in a chemical reaction, what do we call the final stuff? Products. And we call the initial stuff reactants. Okay, so always remember that. So there's the little rule. Notice that the law of Hess still applies, which essentially means is you're going to have to look at the coefficients involved in the reaction. So if one of the substances has a coefficient of 3, you're going to have to multiply whatever that value for delta H is by 3. That's about the only way you can screw this up. So here we go. Let's calculate delta H of the standard enthalpy of formation for the reaction, or standard enthalpy of the reaction for the following reaction. So we've got, C2H6 plus, and I may or may not have fixed yours. You got O2 there? Mm-hmm. Okay, and then carbon dioxide and water? Yep. All right. Does that balance? The reason I ask that is I had to modify mine, and I'm not entirely sure if I modified it correctly or not. Should it be 7 O2s?
All the carbons don't match up.
Okay, so we have to fix that. So let's fix the carbons. I think I cut and pasted a reaction in there, and I didn't fix it. So balance it properly, I guess is what I'm saying. You may just want to rewrite it. Does anyone recognize the calculus symbol in there?
We have not learned that yet.
Oh, really?
No.
Really?
Yeah.
We're doing it like sometime
Soon. So I'll be your first introduction to sigma, the capital sigma. Oh, you guys had sigma before? Oh.
like some theory before.
Oh, okay.
We did it last year.
Okay. So algebra 2 maybe? Ah, well, so you already know capital sigma. You learned lowercase sigma in this class. You don't remember that, but that's okay. All right, so what did you guys get for a balanced equation there? Just tell me the coefficients.
2, 7, 4, and then 6.
That's what I have. 2, 7, 4, 6. You guys all hunky-dory on that?
Yep.
Sorry about that. Also, please pay attention to your states of matter. So, for example, I don't know where water shows up. I'm sure it shows up in that one in the middle of your book somewhere. Oh, you're not there. I think water's under oxygen, believe it or not. Weirdly enough. Yes, it is. Notice that water has 2 different enthalpies of formation depending on whether it's a liquid or a gas. So there's another place that you might mess things up is not paying attention to the right state of matter there. So here we go. Well, the handy-dandy little equation, as you guys know, and I'm going to write all this out, and it's going to look like really hard. It's not. Okay, and in this case, it's C2H6 plus O2, yielding carbon dioxide and water. Liquid, gas, and I think this was a gas. What was it, 2, 7, 4, 6? Okay, so my products are the carbon dioxide and waters, right? So I'm going to have to multiply whatever carbon dioxide is. Did you guys find it yet? Negative 390. Yeah, that's what I'm saying. Negative 393.5 kilojoules, right? Yes. Okay, and we're going to have to multiply that by 4 plus 6 times, and liquid water is like 283 or 285 or something like that. 285.8. Negative, right? Okay? And so that's what that's going to look like. And then we're going to subtract from that the, what is that? Ethane. No, it's not ethane. That's weird. It is ethane. All right, anyway, what is that one?
Negative 84.68.
And then we're going to add to that the oxygen, which is 0. And I'm going to actually write that up there just so that you guys know that we addressed it, that we looked at it. And there you go. You come up with an answer for the first set of brackets. You subtract from that your answer for the second set of brackets. And by golly, you guys have yourselves your delta H of reaction. Yes.
So will they give this to us in the problem when they ask for it, or will they give us a chart?
Well, they've been embedding these in a question. I haven't seen a chart. They've never had a chart like they used to have for the reduction potentials. They actually used to give you a chart for that. This, it's always been embedded in a problem somehow. Or you knew what they were because of other things. Now, I'm assuming that you guys can all do math. You can verify, but I got negative 3119. And again, you can verify. 6, 8. Yep, I have. They're occasionally between textbooks. They have slightly different values. So I know in the past sometimes I've had to modify, but I took this straight out of your book. So. I don't know. I feel like 6 minutes. Might be less.
Like 2.
Okay. I am going to talk about this next piece, okay? There's another example down there, right? Yeah. It says, determine the enthalpy of formation of sucrose. Well, it gives you the reaction, right?
Yeah.
Okay. Now, how are you going to find the enthalpy of formation of sucrose? What else did I give you? I gave you the enthalpy of the reaction, right? So essentially, I'm just pointing this out. Okay, this could be written this way, right? Okay, so essentially what is happening is you're missing this. Does that make any sense? You're missing one of the reactants. You're given the oxygen. You already know oxygen. You're given the enthalpies of the products. You were given the enthalpy of the reaction. It's just an algebra problem you're solving for X. Does that make any sense? Okay, because I know the first time that you guys run into that problem, sometimes people panic and go, how am I supposed to do that? Well, I just kind of showed you how. We have just finished chapter 6, by the way. Give yourselves a little round of applause. I think I broke the assignment down into 2 parts. Is that right? I'm pretty sure I broke the assignment down into 2 parts. I think the first part was up through the heat capacity of a bomb calorimeter. The second part starts with Hess's law. So now you can do the entire, both sides of the assignment, or both parts of the assignment.
Good job, everyone, working hard.
It's the thing on the side. Right there. Or not.
No, I know. They were the different parts. Hold on.
Ah,
For the solid acid part, did you give us like...
It's fine.
no, I was just looking to see when it was. Would you like this back? The thing on the side. There is no thing on the side. Oh, on the side and the top.